So I am Dr. R. Srinivasan from first year engineering BTech, Department of Chemistry. So today we will see, continuing seeing the problems. Last video we have seen water chemistry problems. Today we will see in electrochemistry applications and problems, applications of electrochemical series and problems related to standard EMF of the cell. Okay, this is problems from electrochemistry, which is in module 1, electrochemical series applications and problems on standard EMF of the cell. Electrochemical series is also called EMF series. EMF series. So this is course outcome 2. Utilize electrochemical cell parameters under given condition for calculating EMF and electrode potential of cell. This is Bloom's taxonomy applied. Okay. What is electrochemical series or EMF series? Just a brief before seeing the application of it. Knowing the standard electrode potentials of the metals may be arranged in the order of their electrode potentials from highest negative to highest positive to form a series which is called electrochemical series or EMF series. Okay, so this is that series: metal ions, metal ions per metal. This is in reduction form. Okay, that is the convention to take reduction. Even though the metal may undergo oxidation according to its electrode potential, but we represent only the reduction. So this is half cell reaction, reduction half cells reaction. And this is standard reduction potential. So if you see the standard reduction potential from lithium to fluoride, it is fluorine fluoride, it is arranged and it is minus decreasing, that is minus value comes to 0 and then plus value increases. So basically the values are increasing in the increasing mode. Okay, minus 3.4, 2.9, minus 2.8, increasing mode, 0 and then plus 0.34 like that. So this is an example of a EMF table. Okay, EMF series or electrochemical series. In this, stronger reducing agent means more rapidly gives electron or having more negative. For example, lithium, more negative. Whereas fluoride, fluorine, here more positive, stronger oxidizing agent, more rapidly accepts electron. Means, what is meant by reducing agent? It oxidizes itself to reduce the other species. That means it rapidly gives electron, oxidizes itself to reduce the other species. So it's a stronger reducing agent if it has higher negative reduction potential. Okay, whereas higher positive, more positive or stronger oxidizing agent means it reduces itself to oxidize the other species. So it rapidly accepts electron to get reduced in order to oxidize the other substance. Okay, now we comes to applications of electrochemical series. So there are some important applications of electrochemical series, including the calculation of standard EMF of the cell. E0, we call it as E0, standard. This E0, this is for representing standard. This is saying EMF, standard EMF of the cell. Okay, can be calculated if the standard electropotential values are known. So we use the formula E0 cell is equal to E0 right minus E0 left, or E0 cell is equal to E naught reduction minus E naught oxidation. What is left to right in our cell representation? Normally, for example, we take Daniel cell representation. This is example. Zinc undergoes oxidation in that. So zinc we write in the left, and then with concentration 0.1 molar. Sorry. 1 molar. Okay, and then salt bridge representation. Then copper undergoes reduction. Copper. This is also 1 molar. So here this single dash represents interface between zinc solid and zinc sulfate, zinc plus 2 ions of 1 molar concentration. Okay, this 2 dash represents salt bridge. That means the two electrolyte parts are interconnected by a salt bridge, which will balance the charges of the cell by exchanging the anions, cations, K plus or Cl minus based on the charges required. This is anode, this is cathode. Zinc anode, copper anode, zinc oxidation, anodic oxidation, copper reduction, cathodic reduction. So again copper interface with copper solid metal. Okay, so this is represented by single dash. Double dash means salt bridge. Okay, double dash represents salt bridge, which is the function of salt bridge is to balance the charges balance the overall charges. Okay, so E right means, or you can say E naught of reduction, E naught left means E naught of oxidation. So standard EMF of the cell is equal to standard reduction potential of reduction reaction minus of standard reduction potential of oxidation reaction. The next application is relative easy of oxidation or reduction. So metal on top, that means negative values, or we have seen most negative value or getting most easily ionized or oxidized. For example, lithium plus for lithium we have seen. Higher the value of standard reduction potential, positive value, greater the tendency to get reduced. This we have seen in the fluoride. Fluoride. Okay, this is what we have seen here. Sorry. Fluoride. This is high negative, high positive. Okay. So lithium metal has high negative value minus 3.01 and shows higher tendency towards oxidation. Fluorine has higher positive value of standard reduction plus 2.87 and shows higher tendency towards reduction. Okay. So lithium tend to undergo oxidation easily, and thereby it reduces the other substance. You know that there are a lot of reducing agents, lithium, aluminium hydride. Okay, there are lithium containing well-known reducing agents are there. Fluorine tend to undergo reduction, but it oxidizes the other species. Okay. Okay, next, displacement of one element by the other. Metals which lie higher to the hydrogen in the EMF series or electrochemical series can displace those elements which lie below the hydrogen in the series. For example, again this is in Daniel cell. Okay, zinc is having negative 0.76 volts. So copper is having plus 0.34 volts. So copper is metals lie higher in the hydrogen, they can displace those elements which lie below the hydrogen in the series. So copper is actually displaced from the copper 2 plus solution. Okay. Zinc will displace copper from the solution. Okay. So this is the reduction, standard reduction potential of zinc minus 0.76, copper plus 0.34. So next application of EMF is calculation of equilibrium constant. So we know that delta G naught is equal to minus NF E naught. Minus delta G naught is change in Gibbs free energy. If delta G naught is positive, the reaction is non-spontaneous. Okay, if delta G naught is negative, then the reaction is spontaneous. Okay, we can say spontaneous or feasible. Another word of spontaneous is feasibility. Feasible reaction is feasible, like that. So, and we also know delta G naught is equal to minus RT ln Q, or ln equilibrium constant K. So minus NF E naught is equal to minus RT ln K. So this cancel. So NF log K is equal to NF E naught. NF into E naught by 2.303 RT. This is how it comes. So which is given by, at standard conditions, it becomes 2. At standard conditions, 2.303 RT by F is nothing but 0.0591. N varies according to the reaction system. So N into E naught by 0.0591 volts. 0.0591. Okay. So from the value of standard electrode potential for a cell reaction, its equilibrium constant can be calculated. Okay. Next, hydrogen displacement behavior. Okay, metals with negative reduction potential, that is metals above hydrogen in the EMF series, will displace the hydrogen from an acid solution. For example, zinc, you know, it is having minus 0.76 volt. So zinc plus H2SO4 dilute gives ZnSO4 plus H2. Okay. So this reaction, hydrogen, is possible because zinc is having negative potential, electrode potential. Whereas if you go to metals lying below the hydrogen in the EMF series, will not displace hydrogen from an acid solution because Ag, you know, plus similarly copper plus H2SO4 does not give copper sulfate plus hydrogen, won't give because of plus 0.34 volts copper, we know, electrode potential. Okay, so metal with positive reduction potential, that is metal placed below hydrogen in the EMF series, will not displace the hydrogen from an acid solution. Okay. Okay. Next application of EMF series, predicting spontaneity or feasibility of redox reaction. Spontaneity of redox reaction can be predicted from E naught values. We have seen already delta G naught is equal to minus NF E naught. If E naught of the cell is positive, the reaction is spontaneous or feasible, because delta G will become negative. If E naught of the cell is negative, then delta G positive, so reaction is non-spontaneous or not feasible. So in general, an element having lower reduction potential can displace another metal having higher reduction potential from its salt solution spontaneously. This also we have seen. Okay, now we come to the calculation. We will come to the problems in electrochemistry. First, calculation of standard EMF of the cell. So, what is the problem? Calculate the EMF. Calculate the EMF of voltaic cell, iron 2 plus aqueous, copper 2 plus by copper. So, here this is clearly oxidation iron. This is reduction. We have seen the representation. This is salt bridge. Okay. Now, this undergoes oxidation iron. Okay. Oxidation. Copper undergoes reduction, more positive. Okay. Copper undergoes reduction. So, what is the formula for standard EMF? This is a type of electrochemical cell or voltaic cell. E naught cell is equal to E naught reduction minus of E naught oxidation, which is equal to E naught copper 2 plus by copper minus of E naught Fe by Fe 2 plus, which is equal to 0.34 minus of minus 0.44. So, standard EMF of the cell is equal to 0.78 volts. Okay, this is the answer for this question. Next, calculate the EMF of a cell if the reduction potentials of the cell are this minus 0.763 and 0.337. Here, even though the metals are not known, they are not given, but from this standard reduction potential values, we know which undergo oxidation, which undergoes reduction. So, this is positive reduction. This is negative oxidation. So, EMF of the cell, E cell is equal to E naught cell is equal to E naught of reduction minus of E naught of oxidation, which is equal to 0.337 minus of minus 0.763. So, which is equal to 1.1 volts. E naught cell, which is equal to 1.1 volts. Okay. Okay. Next, predict whether the reaction Ag plus 2 Ag solid plus zinc 2 plus gives 2 Ag plus zinc sulfur. This reaction, given reaction, is feasible or not. So, just now in the application of EMF series we have seen, we have to check whether we have to check whether this EMF of the cell reaction is positive or negative. Then we can say, based on delta G naught is equal to minus NF E naught. So, if E naught is positive, delta G not negative, then spontaneous, or we can say feasible. Okay. If E naught is negative, then delta G naught positive, then non-spontaneous or not feasible, reaction not feasible. So here, if you take what is undergoing oxidation here, Ag, reduction is zinc. So E naught of zinc 2 plus Bor zinc minus of E naught of Ag plus Ag. So which is equal to minus 0.76 minus of, for the reaction given, in this reaction, zinc is undergoing reduction, Ag is undergoing oxidation. So EMF E naught of cell is equal to reduction first, that is E naught of zinc 2 plus by zinc minus of E naught of Ag plus by Ag. Okay. So even though it is undergoing oxidation, we write in the reduction this one. Okay, is equal to minus 0.76 minus 0.80. So which is equal to minus 1.56 volts E cell. So we know that if E naught is negative, delta G becomes positive, non-spontaneous, not feasible. So the reaction is not feasible because delta G naught is positive. Why delta G naught is positive? Because of E cell negative. So the reaction is not feasible. That is the answer. Not feasible. Okay. Next. Predict which of the following reactions will be spontaneous with the help of standard reduction potentials. Okay. Iron plus 2H plus gives Fe2 plus hydrogen. So here, if you see, iron undergoing oxidation, iron oxidation, iron 2 plus. Similarly, hydrogen undergoing reduction, 2H plus more hydrogen. This is reduction. So we know that this is minus 0.444 E naught value. This is standard is 0 volts. Okay. So now E naught cell is equal to E naught of reduction H plus hydrogen minus oxidation, standard reduction potential of oxidation. So which is equal to minus 0 minus of minus 0.44 volts. So E naught cell is equal to plus 0.44 volts. So that shows that delta G is negative. So the reaction is feasible or spontaneous. We have seen in the application that iron is having iron plus H2. So for iron is having negative 0.44 volts. So it gives iron sulfate plus hydrogen. Okay. So whereas second, by seeing itself we know it is not possible. Okay. Anyway, we will see from the second one also we will see. copper undergoes oxidation. So E0 cell is equal to, first which is undergoing reduction, hydrogen. E0 H plus by of hydrogen minus of E0 of oxidation, which is undergoing oxidation, copper. So which is equal to 0 minus 0.34. So E0 cell is equal to minus 0.34 volts. So we know that here delta G is positive. So the reaction is not feasible or non-spontaneous. Or we can say the reaction is not feasible because of delta G positive. So this is spontaneous reaction. This is non-spontaneous reaction. Okay, next. Give the representation of a standard cadmium copper cell. Write the electrode and cell reactions and calculate the standard EMF of the cell. Standard electrode potential of cadmium and copper are given. Okay. So first, cell representation. Cell representation. So cadmium negative, copper positive. So cadmium undergoes oxidation, copper undergoes reduction. So cadmium bar, cadmium 2 plus, Sawbridge, copper 2 plus bar, copper. So this is one here, this is, okay, this is the standard representation. Okay, how will you write the electrode reactions? Electrode reactions. Anode, cadmium, okay, anode, oxidation. Cadmium gives cadmium 2 plus, cadmium 2 plus 2 electrons. Similarly, cathode, reduction, copper 2 plus 2 electron gives copper. So overall cell reaction. This is anodic half cell or oxidation half cell. This is cathodic half cell or cathodic reduction half cell. Now overall reaction is cadmium plus copper 2 plus gives cadmium 2 plus copper. Okay, this is the electrode reaction, electrode cell reactions. Standard EMF. So standard EMF of the cell is equal to E0 copper 2 plus by copper minus of E0 cadmium 2 plus by cadmium, which is equal to 0.34 minus of minus 0.4, which is equal to EMF of the cell standard 0.74. This is the answer. Okay. Next. Write the cell representation, cell reaction, and calculate the standard EMF. Cell representation, cell reaction, and standard EMF of a nickel Ag cell. Standard reduction potential of nickel and Ag are given. So negative, this is nickel undergoing oxidation. nickel undergoing oxidation. Ag positive reduction. So more positive will undergo reduction. Ag will undergo reduction. Okay. More negative will undergo oxidation. More positive will undergo reduction. So we know this. Okay. So now how will you? So Ag undergoes reduction because of positive 0.8 volts electrode potential. Nickel undergoes oxidation because of negative electrode potential. Okay. Now cell representation. Nickel bond, nickel 2 plus. Okay. 2 plus 1 molar. Nickel bar, nickel 2 plus. Salt bridge. Then Ag plus per Ag. This is also okay. So this is the cell representation. Now electrode reactions or cell reactions, electrode reactions. Anode oxidation. Nickel gives nickel 2 plus plus 2 electron. Cathode reduction. So Ag plus plus electron, 2 Ag plus 2 electron gives 2 Ag. Okay. So overall cell reaction. Overall cell reaction. So this is anodic half cell or oxidation half cell. This is cathodic half cell or reduction half cell. Overall cell reaction is nickel plus 2 Ag plus gives nickel 2 plus plus 2 Ag. Okay. So this is how the overall cell reaction will come. Now standard EMF. Standard EMF of the cell, E naught cell is equal to E naught Ag plus by Ag minus of E naught of nickel 2 plus, which is equal to 0.8 minus of minus 0.25, which is equal to 1.05 volts. That is standard EMF of this cell. Okay, 1.05 volts. Fine. Okay, next. Calculate the equilibrium constant for the reaction Fe3 plus plus 3 iodide gives Fe2 plus plus I3 minus. The standard reduction potential for Fe3 plus and I3 minus is given. So this is, both are positive, but still this is more positive. So we'll undergo reduction. More positive will undergo reduction. That means here this is reduction. Less positive will undergo oxidation. That means this is here oxidation. Okay. Okay. So we have seen already in the electrochemical series applications, delta G naught is equal to minus NF E naught, which is equal to minus RT ln K. So K is equilibrium constant. So ln K is equal to minus NF E naught by RT. Okay. sorry, minus, இங்க இருக்கிற minus. So, log K is equal to N E naught divided by 0.0591. Okay, fine. So this is how the formula has reduced. So now what is the E naught? E naught is equal to 0.23. How it came? It is E naught of reduction 0.77 minus 0.54 volts gives 0.23 volts. So using this formula, we can write N is equal to 1. N is equal to 1 because both are 1 electron is involved. So 1. So log K is equal to, just substitute E naught by this one. Log K is equal to 3.892. K is equal to, this is 7.9 into 10 power 3. Okay, next. So these are all the reference books. Okay, with this video is over. See you in the next video, the continuation of problems in electrochemistry. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.